Welcome friends. Now I will teach you the remaining 3 units of structural analysis. Now up to MSc mid-semester, your first 3 units are completed by Dr. V.S. Patil and myself, Dr. S. Santande. I am head of Applied Mechanics Department. So I will try to complete your remaining 3 units. Actually, as per our syllabus, the remaining 3 units, the syllabus is heavy that way because 4th unit consists of 2 methods, slope deflection method and moment distribution method. And 5th unit again consists of 2 methods, flexibility method and stiffness method. And the last unit is on influence line diagrams for determinant structures. So today we will start with 4th unit, that is slope deflection method. Now basically the slope deflection method is a displacement type method. So later on we are going to study in detail force methods and displacement methods in the next unit. So this slope deflection method as well as moment distribution method, both these methods are of displacement type or stiffness type methods. So once you understand the slope deflection method, you will understand moment distribution method as well as the stiffness method also. Now this slope deflection method is basically used for analysis of indeterminate structures, all types of indeterminate structures, say propped cantilever beam, fixed beam, continuous beam, then portal frames, simple frames. So all types of indeterminate structures we can solve with the help of slope deflection method. So basically this method, to understand the procedure of this method for analysis is very simple. It's not difficult at all. But you have to do the practice for solving various types of problems. So if you solve the number of problems by using this method, then only you will understand this method in a proper way. Now what is slope? Why this method is called slope deflection method? Because in this method, slopes and deflections are considered as unknowns. So slopes and deflections at the joints are considered as unknowns. So that's why this method is called slope deflection method. It is not like to find out the slopes and deflections in case of determinate structures, but this is a slope deflection method which is used for analysis of indeterminate structures. Now slopes and deflections means displacements at the joints are taken as unknowns. That means kinematic degree of indeterminacy. Kinematic degree of indeterminacy is to be worked out. And I think during the first unit only you have learned how to calculate static degree of indeterminacy, how to calculate kinematic degree of indeterminacy, what is statically determinate indeterminate structures, what is internal degree of indeterminacy, external degree of indeterminacy, etc. And here in this method the kinematic degree of indeterminacy is required. In earlier method, say the strain energy method, where we take the forces as unknowns. So that method is categorized as a force method or flexibility method. Here the displacements are considered as unknowns. So later on we will study in more detail the displacement type method, because the displacement methods are more suitable for programming purpose. So that we will see in matrix methods of structural analysis in the next unit. Okay, now here slopes and deflections are considered as unknowns. Kinematic degree of indeterminacy of the structure is to be calculated, and finding out kinematic degree of indeterminacy is very simple. So what is kinematic degree of indeterminacy? So these are the number of independent joint displacements. The number of independent joint displacements are called kinematic degree of indeterminacy or degree of freedom of the structure. So that is very important, independent displacements. So only we have to count the independent joint displacements in order to find out kinematic degree of indeterminacy. Now here, see, before we start to solve the problems, how the slope deflection equations are to be developed. Actually, these slope deflection equations are to used to find out the final end moments at the end of any member. Suppose we have a continuous beam. If we have a continuous beam, or if we consider one span, intermediate span of a continuous beam, say AB. AB is a span, single span, or an intermediate span of a continuous beam, or say AB is a fixed beam. So now here, in order to develop the slope deflection equations due to the various degrees of freedom or displacements when the beam undergoes. Suppose A undergoes a rotation theta A, only rotation at A, theta A, then we know the fixed end moment developed at A is 4 EI by L theta A, and at B it is half of that, 2 EI upon L theta A. Actually this you might have been learned in fixed beams or method of consistent deformation earlier. We can derive these formulas. That means when if a beam AB is fixed beam or an intermediate span of a continuous beam, and the end A undergoes a displacement theta A, a rotation theta A, then fixed end moments developed at the end where the displacement rotation occurs, 4 EI by L theta A, and at the other end half of that, 2 EI upon L theta A with same sign. Similarly, if end B undergoes a rotation theta B, if end B undergoes a rotation theta B, then fixed end moment developed at B is 4 EI by L theta B, and the further end it is half of that with same sign, that is 2 EI upon L. Actually this is the carryover theorem that we will see in the moment distribution method. Then suppose one of the support undergoes a vertical displacement, or there is a settlement of the support, or we can say sinking of support occurs. Now due to sinking of support, the fixed end moment developed at both ends we can calculate if delta is the level difference. Maybe either left support down or right support down, or the level difference is delta between the two supports. If we work out this delta level difference, if left support is down, both end clockwise moments are developed, and which is equal to 6 EI delta upon L square. And if the right support goes down, then both end anti-clockwise moments will be developed, and the value will be again same, 6 EI delta upon L square. So depending upon which support goes down, which support sinks down, the moments will be either clockwise or anti-clockwise. And again, the beam is also subjected to a loading, external loading. And due to external loading, say fixed end moments, MFAB and MFBA. So these are the fixed end moments due to the external loading. Now, how the slope deflection equations, though, what will be the final moment? So final moment will be due to the combined impact plus. If we take this, the MAB here, the final moment is nothing but sum of this, and MBA here is nothing but sum of all these moments. And the sign convention that we are going to follow is clockwise positive, anti-clockwise negative. So that means the MAB is equal to 4 EI upon L theta A plus, so this value, then 2 EI upon L theta B, 2 EI upon L theta B. So this plus this may be plus or minus, so plus or minus 6 EI delta upon L square. That depends upon whether which support is down. Either if left is down, plus, if right is down, minus. And due to loading, generally left hand is anti-clockwise. Or here also we can say plus minus MFAB. So plus minus MFAB. So this equation is called slope deflection equation. So we get the final moment. If we know the slopes and deflections, then the final moment can be calculated easily. Let's take this 2ei upon L common. So this becomes 2 theta A plus theta B plus minus 3 delta upon L, and this is, let's keep this separate, MFAB. So slope deflection equation uses the final moment at A or beam AB when it undergoes rotations and deflections simultaneously. So this is the moment by using slopes and deflection. Similarly, MBA is equal to 2ei upon L, 2 theta B plus theta A plus minus 3 delta by L plus minus MFBA plus minus MFBA. So it's very simple to write down the slope deflection equations. So this we have written for span AB. Suppose you have another span, if it is a continuous beam, and your span is say BC. If you have a second span BC, how you will write this equation, that MBC equal to 2ei upon L into bracket, so B is first, 2 theta B plus theta C plus minus 3 delta by L plus minus MFBC. So MFBC, that is fixed end moment due to the loading at B. Similarly, MCB equal to 2ei by L into bracket 2 theta C plus theta B plus minus 3 delta by L plus minus MFCB. So that means for any span we can write down these slope deflection equations very easily. So after solving one or two problems, so you will remember these equations, or you can write down these equations very easily. So no hard work is required to remember this equation. So these equations are called slope deflection equations. These equations are called slope deflection equations. So these equations are called slope deflection equations. That means these slope deflections equations are very important. So in order to find out end moment, so the unknown displacements, that is theta A, theta B, delta, etc. must be calculated first. So that means this method is very simple. So I will tell you first the procedure, how to solve this. We'll develop the procedure, then I will give you the list of the fixed end moments due to the standard loading. So how to calculate the fixed end moments due to the standard loading, and then we will see the problems on this. Now next, let's see the procedure. Now, in order to understand the procedure, step-by-step procedure to solve the problems by using slope deflection method, so we'll consider one example. So let's consider one example, say a continuous beam ABC. A continuous beam ABC. So this is A, this is B, this is C, subjected to any type of loading. Say any type of loading. ABC is a beam subjected to any type of loading. Now here, what is the first step? The first step is to identify unknowns. So now unknowns here, we know the slopes and deflections at the joints are taken as unknowns. Slopes and deflections at the joints are taken as unknown. Now there is no question of deflection here. So end A is fixed, that means theta A is 0. End C is also fixed, so theta C is 0. And delta is 0 everywhere. There is no question of delta. Delta is a sinking of support, normally it is given. So theta A is 0, theta C is 0, only theta B is unknown. Because if you draw a deflected shape, so the deflected shape will be like this. So here it is, if you draw the tangent to the deflected shape, deformed shape. Here tangent is horizontal, here tangent is horizontal, but here you will get a tangent. Means you will have a unknown theta B. So you will have a unknown theta B. Now, the first step here is identify unknowns. So here unknowns, only one unknown, theta B. So theta A is 0, theta C, there is no question of delta, sinking of support. So theta A 0, theta C 0, because A and C both are fixed. Now unknown is only theta B, only one unknown. Now to find out this unknown, the joint equilibrium equation is to be used. Now the second step, let's identify joint equilibrium equation. Joint equilibrium equation. So joint equilibrium equation, that is B is unknown. So at joint B only we have to write down the equation, and that you know very well. MBA plus MBC equal to 0. Because joint B must be in equilibrium, so resultant bending moment at continuous joint B must be 0. That means MBA plus MBC. So at B for span BA, at B for span BC, so MBA plus MBC must be equal to 0. The equilibrium of joint must be satisfied. So one unknown, one equation. Now next what we have to do, next step is develop slope deflection equations. Now let's develop slope deflection equations. Third step, that is, we know MAB equal to 2EI upon L into bracket 2 theta A plus theta B plus minus 3 delta upon L plus minus MF AB. So that we have to develop. Then MBA equal to 2EI upon L 2 theta B plus theta C, MBA theta A plus minus 3 delta by L plus minus MF BA. Then MBC equal to 2EI upon L 2 theta B plus theta C plus minus 3 delta upon L plus minus MF BC. Then the last MCB equal to 2EI upon L 2 theta C plus theta B plus minus 3 delta by L then plus minus MFCB. So these are the slope deflection equations. Now here we have to substitute. So we know this theta A 0, then theta C 0, this 0, and delta is also 0. This is 0, this is 0. Delta terms are also 0. So only theta B is unknown. And these are the fixed end moments that I will tell you how to calculate these fixed end moments due to various types of loadings. Now that means if we know the value of theta B, we will get the final end moments. And once we get the final end moments, then we find out the reactions and then we construct SFD and BMD. Now the fourth step Fourth step, using joint equilibrium equations, using joint equilibrium equations, find unknowns. Here unknown is only one, find unknowns. Here it is theta b. So joint equilibrium equation we have MBA plus MBC is equal to 0. Let's substitute this MBA and MBC here in this equation. These two are to be substituted here, and solving this equation we will get theta b, value of theta b, or directly you can say you will get EI theta b, either theta b in terms of EI, or you find out EI theta b, so that we can directly substitute here. So after getting theta b, then the next step, find end moments and final end moments by using slope deflection equations. By using slope deflection equations. So let's use the this theta b. You substitute theta b here in slope deflection equations and find out final moment. So all these moments we will get now: MAB, MBA, MBC and MCB. So these moments are calculated by using the slope deflection equations after knowing theta b. And after calculating this, next find reactions. Find reactions by using equilibrium conditions. Just by using equilibrium conditions, you find out reactions. And the last step is draw SFD and BMD. Draw SFD and BMD. So this overall procedure to solve the problem by using slope deflection method. So very simple procedure. Identify unknowns. So after solving problems, 2-3 problems, we will understand that identifying unknowns in this method is very simple. Then write slope deflection joint equilibrium equation to find out the unknowns. Just mention this equation. Then develop slope deflection equations. Then using joint equilibrium equations, this joint equilibrium equations, find out theta b, and substituting theta b back to the slope deflection equations, find out end moments. Then after knowing end moments, by using equilibrium conditions, find out support reactions. And finally, knowing bending moment, support reactions, everything, draw SFD and BMD. So the very simple procedure. Now next time what we will do, we will first see the formulas, fixed end formulas for various standard cases, and then we will start solving the problems. So now we will stop and we will continue later on again from here onwards.